Everyone, we're back. This is Michael, and again, I'm here to help you understand the way we approach highlighting passages for the MCAT and how we also approach drawing out information from questions to arrive at the right answer. I promise this video will be shorter than the one before. If you haven't seen that one, I suggest you look at that because I'm just going to be repeating the concepts I introduced in there, and I'll be going through it much quicker, right? So we have passage A. This is JackWestin. We have a couple of questions. This looks more like an organic chemistry passage. All right. Again, the three things for highlighting passages. The highlight should be your summary. If I look at your highlight, if you look at your highlight, you should be able to understand what the passage is saying, capture all the relevant information. Number two, any new noun you see in the passage, highlighted, because they're probably going to give you more information about that now. And number three, your highlights are your reference point. If you have a good highlight, this exam could look more like an open book test for you for most of the questions because the answers will be in the passage, right? All right, let's delve into it. Saturated fatty acids of the carb. This is a new noun, saturated fatty acid in animals include these. You could highlight them with their respective numbers. Personally, I know once I have highlighted saturated fatty acids, I know what I'm going in for. I know where to find them. But hey, let's say we highlighted them, okay? So we highlighted the names and the number of carbons respectively. Propanoic acid is a new noun. That's 30, that's three carbons, it's not branched. Zero means it's not branched, right? The shortest odd chain fatty acid. So it's odd chain, and it's the shortest odd chain. So there's not one chain fatty acid, right? There's seldom esterified to lipids, whereas longer odd chain fatty acids, mainly these, are present in small amounts in animal tissues. So now my first paragraph is good. Long chain fatty acids. That means they're going to give us more information about long chain fatty acids, right? Long chain fatty acids are synthesized within the fatty acid synthase 1 complex in a series of 6 reactions. So they are synthesized within FASI. Now, let me highlight synthesize. So long chain fatty acids synthesized in FASI in 6 reactions. That's enough. I don't have to highlight the rest. Yes, they may be important, but this gives me the snapshot I need. They involve adding 2 carbons. It's important. This is how it happens, right? Carbon units from malonyl CoA is a new noun, highlighted, which is produced from acetyl CoA by acetyl carboxylase, right? In other words, malonyl CoA is the result of the conversion of acetyl CoA by the carboxylase. If I say it a different way, carboxylase converts acetyl CoA to malonyl CoA, right? The structure of malonyl CoA is shown in the figures. There's a structure that's great. The reaction sequence catalyzed by FASI complex. These are the figures. They help us bring us the information. There's not much to highlight here. I may highlight this just in case. I want to come back to this figure. It's not much to highlight there, honestly. Let's go in. All chain fatty acids. They're going to give us more information about all chain fatty acids, right? Can be synthesized from propanoyl CoA, right? From propanoyl CoA. I don't know why I pronounce it like that, but that's, you get what you get, right? Instead of acetyl CoA through alpha oxidation of even chain fatty acids, right? And this is important information, each of this. So it's all chain fatty acids they can be, it doesn't mean that that's not always, synthesized from propanoyl, whatever, CoA instead of acetyl CoA, right? Instead of acetyl CoA through alpha oxidation of even chain. So I might highlight this. The key is I am not trying to highlight every single piece of information. I want something that if a question comes on all chain fatty acids or propionyl-CoA, I can find it, right? Right. So propionyl-CoA can be converted. So this might be something, it's giving us more information about propionyl-CoA, can be converted to D-methylmalonyl-CoA, right? By propionyl-CoA carboxylase, right? Can be converted to D. Actually, let me just highlight this. Highlight this whole thing. Just because, right? That's shown in figure 3. So figure 3 shows us that conversion from NLA all the way to D-methylmalonyl-CoA. We are done with the passage, right? Substituting D-methylmalonyl-CoA for malonyl-CoA introduce a methyl branch into the fatty acyl chain. So this might be important, right? To substitute, actually, yeah, you know what, let's do it. Substituting this D-methylmalonyl-CoA for malonyl-CoA. In other words, if we, the reaction below, if we change D-methylmalonyl-CoA for malonyl-CoA, we get a methyl branch, an additional methyl branch in the fatty acyl chain. So then I was like, okay, what does all this mean? We will find out. To be honest, I've not reviewed this topic unless we're going to go with my idea that if we highlight well, it can become like an open test. So let's see. Based on figure 1, this is our green flag, which carbon in malonyl-CoA is added by acetyl-CoA carboxylase. Acetyl-CoA carboxylase. So those are the two key things. Which carbon? The main question is, okay, there's a carbon that is added by this carboxylase. Which carbon is that? So we go to figure 1, look at it. Yes, there are carbons everywhere, but usually you're looking for a carbon with a double bond because that's the first carbon that's going to be attacked. In any compound in organic chemistry, if something is going to attack a carbon, it's probably going to be the one that has a double bond. Why? Because of the electrophilic activity, the electron cloud that I repeat. All right, so let's look at this. It said, which carbon in malonyl-CoA is added by acetyl-CoA carboxylase? We read in the first paragraph that there's an addition of 2 carbon units from malonyl-CoA to fatty acid synthesis, right? And we read that the malonyl-CoA is produced by acetyl-CoA. I don't know if they have a structure here. They have a structure of acetyl-CoA here. So we're using this structure. I can try and see where in this structure acetyl-CoA is placed, right? If I look at it, the coenzyme is a coenzyme. It's not going to take part in that reaction per se. So where my S starts from backwards, I can trace that here as this is my first carbon, the carbonyl group, right? That's number 3, and number 2 would be this methyl here. Seeing that, that means my acetyl-CoA is going to be in this region. Now, with this, I think we need to know what carboxylase does. Carboxylase, like the name, if I remember correctly, is going to add either a carbon dioxide or bicarbonate. But for MCAT purposes, I think you just have to remember that it adds a carbon dioxide, right? So if it's going to add a carbon dioxide and you already have your acetyl-CoA here, then it means to me that the only carbon it can add to make this complete is 1. Carbon 1. It's not going to add carbon 4 or 5 because of where they are positioned. And carbon 3 and 2 are part of acetyl-CoA that we map over here, right? So then it's going to be carbon 1. Okay, let's see if it's right. So this doesn't need too much. I think the main thing they're asking you here is, what does acetyl-CoA carboxylase do, or what do carboxylases do, right? All right, let's move to the next question. Which of the following shows the predominant product from a reaction of D-methylmalonyl-CoA and a race base? Once I see this is a buzzword for me, race base. So I think basically what they're trying to ask us is, what is race base, or what is a race base reaction? we know racemic reactions have to do with the mirror opposites, like enantiomers, right? So I'm thinking in my head now that, like I told you, I've not reviewed this in a while, but just by knowing that what a racemic reaction is, and this is D-methylmalonyl-CoA, I'm probably looking for L-methylmalonyl-CoA. First and foremost, I'm going to remove anything that doesn't look like methylmalonyl-CoA because enantiomers have the same structure, but they are just different. They're like mirror images. The side chains are rotated in a different, are oriented differently. If I look at this first one, I see my CoA, which I have here, CoA and carbonyl. I see my carboxylate, my, what's it called, functional group. I see that here. But I look at it, there are two H's, right? There are two H's here. Okay, one may say it looks like it, but it doesn't, really doesn't see. Let's count the carbons. 1, 2, 3. That's 1, 2, 3. And the fourth one is the side chain here. They don't look alike, so that is wrong for me. B, 1, 2, 3, 4. The methyl group and our carboxylic acid functional groups have swapped here. This might actually be the answer, but let's wait and see the rest. 1, 2, 3, and then find there's an OH here, so that's a no. 1, 2, 3 carbons, that's 4 here. Oh, this is the same as D-methylmalonyl, so this cannot be the answer. So by elimination, I've come to the answer B. Now, I'm sure you know better than I do how D and L can be deduced. That's a content thing. I can't explain everything here like that, but even by just knowing what a racemic mixture is and the fact that it has to be the opposite, you see, we've come to the answer. This doesn't look anything like D-methylmalonyl. Remember, it has to be the same structure. The only thing is that two side chains will change positions. Usually, I say two side chains because usually the third side chain is an H, like we see here. So the methyl group and our, let me use the annotation so that I'm not confusing anyone. The methyl group here and our carboxylic acid or carboxylate group, they will usually swap positions because this is our chiral set. This is our chiral carbon. You're always looking at the chiral carbon. It has 4 different things connected to it. That is where the switch is going to happen. So it's either the methyl group and the carboxylate, or this whole group over here, the carbonyl group with the CoA, can swap with the carboxylate. It can swap with the methyl group. Like the side chains around our carbon are going to swap, and that's what's going to give us the mirror image, right? So hopefully this makes sense. And I think the first 2 questions we've done have all been really red flag questions, right? They've all been really red flag questions. Let's do number 14. Which of the following can be used to track the reaction shown in figure 3? Let me clear this off our screen so it doesn't confuse us. In figure 3, what are we looking at in figure 3? We are coming from, this is probably what? Okay, we're coming all the way down to D. Okay, all right. So what is going to happen? Let's count our carbons. We have 1, 2, 3 carbons. In our product, we have 1, 2, 3, and 4. That, just by that, I'm going to cancel out its appearance because what is happening is I'm adding a carbon or I'm adding another functional to what I started with. So just by that disappearance. Now, the second part has to do with memorization, right? It has to do with memorization. You have to remember what peak is associated with the carboxylate dysfunctional. If it was an if it was an ester, then you have to figure out which peak relates to an ester. So let's see. I'm just going to choose C, not because I know the answer, but I want to just review the answer. So I didn't know this answer. I'm just choosing it because, right? But this is more of a memorization thing than a conceptual thing. You have to memorize the numbers of the different functional groups, right? The peaks. where they appear, right? Okay, so let's see. A broad peak around this is characteristic of an OH or NH, stretching vibrations, right? So by just looking at that, 3,000 per centimeter is for alcohol on amine, right? Let's see. C says a sharp peak around 1,300 per centimeter indicates a CO stretch of vibration. So if you know this one, if you memorized it, this question would have been easy for you. The only thing you needed to decide is whether it's going to disappear, it's going to appear, right? Disappearing is because I removed that because we are adding a carbon. There are 4 carbons in the product. There are 3 carbons in the reactant. So there's no way the peak can disappear, right? All right, let's do 41. Linking two acetyl units to form a 4-carbon chain by Phys requires way to show how I approach questions. So based on the passage, which of the following would not likely be used in the synthesis of nucleic acid? Nucleic acid is 18, and 1, that means that's like 1 branch somewhere. 18 means it's even, right? So that means anything that is only used in odd chain has to be out. 18 for me shows that it's an even chain fatty acid. So acetyl-CoA can be used. That's great. I think that's true. Malonyl-CoA from the first paragraph read it. We are using acetyl-CoA, which is transformed to malonyl-CoA, and malonyl-CoA is now transformed into the fatty acid. So these two can be used. If I look at propanol-CoA, let's see, when was the first time I saw that? Okay, that was here. Propanol-CoA can be converted to, let's go back, odd chain fatty acids inside from propanol instead of acetyl-CoA. There's nothing in the passage that says propanol-CoA from even chain. See, so with my highlights, even when I lost my train of thought, because I highlighted odd chain fatty acids here, I was able to come back to see what are the things do I need for odd chain. Yes, the question is asking about even chain, but it means because the question is asking would not likely, which is a key word here, I want to make sure that I know what is used for only odd chain fatty acids. And from that, final core is the only thing here. Steroid CoA, I didn't think it was even mentioned, and I'm not going to worry myself about that. What was mentioned here was final CoA. And like I said, a good highlight will make this an open book test. Yes, that's right. A good highlight will make this an open book test. And hopefully you're able to learn something from this one too. All right. Thank you very much. I'll see you soon.